When we first learned about the derivative, we had this limit definition of the derivative, which helped us find the derivative at different points. And that was pretty good. That was awesome and really miraculous that we could find an instantaneous rate of change. But we're now very happy to get some shortcuts. We've had the power rule shortcut, we've had the exponential rule shortcuts, and a few others. And today we're going to learn some really important ones, the product and quotient rules. And so remembering that, like on a calculator, you have sums, difference, product, and quotient. And so we know sum, different, product just always means multiplication, and a quotient means division. So functions which have these two operations, products and quotients, that's what the rules that we're going to talk about here apply to. So at this point, derivatives that we feel good about, like that we have shortcuts for, are power functions. So any base x to a power, or exponential functions. And we've talked about the difference between these, even though they look pretty similar sometimes. That's where we have some base a, and then the exponent has some variable expression in it. And then we also know how to do sums or differences. Both of these guys, combining them. We know how to do constant multiples. We could take the derivative of 5x to the third, for example, or 7x to the 1/2. This has a constant multiple, as well as a power function, a constant multiple, another power function. And we just take the derivative by sort of pulling this constant multiple to the side for a minute and concentrating on the derivative of this. And we also know sine and cosine, how to take the derivatives of those. So that's awesome, that's a lot, but it's not nearly as many as we need. So these are good shortcuts to start with. So we want to think forward a little bit to derivatives that we still want to learn. And this will be when we have a function which involves products. So something like x squared times e to the x. We don't yet know how to find the derivative of this, or a quotient. So maybe we have a function y equals x squared over e to the x. And again, we don't really know how to find the derivative of this yet. So this is going to be what we focus on here. And in the future, we're going to want some other things, like there's functions which are compositions of functions. This is where you're sort of putting one function inside of another, like y equals e to the x squared plus 2 would be an example of that. This is a function which you're really composing the function e to the x with the function x squared plus 2. We'll talk a lot about this one. This is a pretty special one. We're not going to talk about it in this video, but this is one that gets used quite a bit, and we have a rule for it called the chain rule. And once we learn the chain rule, it really opens up to a whole universe of functions that we can deal with. We also are going to see some more trig. We don't yet know how to find the derivative of tangent of x, or secant, or cosecant, or cotangent. Those are all functions that we want to know how to find the derivative of, as well as logarithms, specifically natural logs, and we'll even learn some derivatives shortcuts for inverse trig functions. But here in this video, we're going to just focus on products and quotients. We'll get to the rest of these later. So say that we wanted to find, the derivative of f of x equals x squared times e to the x. This is definitely a product of two functions. And so we would maybe guess, or possibly hope at least, it would be very nice if the derivative of this function was 2x times e to the x. So just taking the derivatives of each factor. So we do have a question about this. Is it possibly that the derivative is just 2x times e to the x? So here is the function that we want to find the derivative of. This is that function, and we can kind of see how it behaves. It looks like it's climbing. It has a maximum right here, and then starts going down, hits 0, 0. That's a minimum, and then it just takes off from there like a rocket. The climb here is not that steep, but it is positive, and then a negative derivatives, and then a 0 derivative right here, and then a lot of positive derivatives. So we kind of have an idea of what the derivative should at least look like. I'm going to give you two options for the derivative, and I want you to choose which one it should be. So remembering how this one builds up, decreases, and then shoots up. Could the derivative be this guy right here? Could it be this guy right here? Well, let's look first where the derivative should be 0. There's 2 times in the original function that we see the derivative being 0, or sort of a topping out right here and a bottoming out right here. Desmos is the one that found that for me. I kind of could tell that it was a little, this is like a very teeny tiny little hill, but it is a hill. I can tell this is the top, and Desmos gave me that point, and then this is the bottom of a valley here. So the derivative needs to be 0 here, and it needs to be 0 here. Does that work in this case? No, this can't be it, because at -2, the derivative needs to be going through 0, and this one's not. Okay, let's check out this one here. The derivative does go through -2. That's good. And it does go through 0 right there. That's good. Okay, so is it climbing? Is it positive? Is the derivative positive before -2? And it is. It's above the x-axis, so this derivative is positive, and then it hits 0. And it needs to go down negative, and it does until we get to 0, and then it needs to be 0 and then go positive. So it looks like this is actually closer to what the derivative should be than this. So let me tell you what this function up here is. This is y equals 2x e to the x. So unfortunately, the one that we really hoped would be the derivative is not the derivative. So we can immediately answer, we were guessing, hoping, praying that maybe this would be the derivative, and the answer is no, unfortunately. So this actually is a graph of the derivative. What is this function? This is the function y equals 2x e to the x plus x squared e to the x. So this here is the derivative of this function here. And it's a little bit more complicated. We have to think, where did this even come from? So think of a good mystery where the murder in this murder mystery, all indications, all clues point to one particular person, but in the end, it's actually someone completely different. And that's what's going on here. We have a function. We really want its derivative just to be the derivative of each factor. It's the obvious choice, but it's not the true derivative. So this is why we have a special rule called the product rule. This is actually going to be our derivative here. And so in fact, yes, someone we didn't really suspect at all would be the derivative is. And so we need to learn where this came from. How did this derive from this function here? So we've just learned that if f of x equals x squared e to the x, then the derivative is 2x e to the x plus x squared e to the x. And so I'm going to give you the product rule, and we'll look at some examples. A little later, we will talk about why and where it even came from. It seems like it just gets plucked out of thin air, but there's definitely, just like all things in calculus, there's some for sure definite reasons for why it is the way it is. Okay, the product rule is going to tell us that the derivative of, say we have a function f times a function g, like how here we have maybe the f could be x squared and the g could be e to the x. So two different functions that are being multiplied together, and they are becoming this new function. The derivative will be, I'm going to write it f times g prime plus f prime times g. So this rule, the product rule, tells us when we're taking the derivative of two things multiplied together, you will take just the first factor, just regular, times the derivative of the second, plus the derivative of the second, no, the derivative of the first times the second. So that's what was going on here. Here we had this piece, x squared, and this piece, e to the x. So when we take just the regular first piece, so that's x squared, times e, the derivative of the second piece, the derivative of e to the x is just e to the x. This is f times g prime. And then we have the derivative of the first. So this is the first one, and that's 2 times x times just regular, the function g. And if we wanted to make sure that it fit the pattern, we would move this over. These movements, of course, are no big deal because everything's just being added. But this tells us that we have f regular times the derivative of g plus the derivative of f times g regular. And that's where all of this came from. So this is a rule that you'll do so many times that you're going to just start remembering it. Let's look at a few more examples though. So say that we have this one. So I have a function y equals x squared plus 7x times 3x cubed minus 2. And each of these I know how to take the derivative of separately, but importantly, the derivative of y, or dy dx, or y prime, is not just going to be 2x plus 7 times 9x squared. I can't just take the derivative of each part and multiply them together. We already know that that doesn't work, that we really truly have to follow the product rule and do all these steps. This is going to be what the derivative is. So we'll say dy dx is just regular first, so that's x squared plus 7x times the derivative of the second, which is 9x squared, plus the derivative of the first, 2x plus 7, times regular second. And that's it. This is the derivative of this guy here. Okay, our next example is going to be find dy dx if y equals x cubed minus 3 minus 5x squared times sine of x. And this one would be a good one for you to try before you see the solution. So just go ahead and pause the video and get the derivative of this one on your own. It's obviously a product. We have this times this, and see what you get. Okay, so you've paused the video and you've found the derivative, and now we'll do it together just to see if we get the same thing. So the derivative will be regular first, so we'll just rewrite that first factor, x cubed minus 3 minus 5x squared, times the derivative of the second, so the derivative of sine x is cosine x, plus the derivative of the first part, so the derivative of this, which will be 3x squared, and the derivative of negative 3 is just 0, and then we get a negative 10x, so minus 10x, and then just regular second part, so times sine of x. And this is it. This is the derivative. We see that we have regular first, derivative of the second, plus the derivative of the first, regular second. So when you have a function that's the product of these two factors, you should be looking for 4 parts, and then right in the middle is going to be a plus sign. We'll do another one. We want to get a lot of practice with these. So say we want to find the derivative dy dx if y equals 5 times the cube root of x times cosine of x. And this one would also be a really good one for you to try on your own. And so go ahead and pause the video and try this guy, and then we'll do it together. Okay, we're going to find the derivative of this guy right here, and we're going to use the product rule. We have a product, and we're treating it as the product of these two factors here, and so we will take the regular first, which is 5 times cube root of x, times the derivative of cosine x, and the derivative of cosine x is negative sine x. This is why we want to be super careful about parentheses, because if we didn't have parentheses, this would look like a subtraction here, but the parentheses will indicate that we're doing a product, a multiplication. Okay, next comes a plus sign, this plus sign right here, and then we take the derivative of the first, 5 cube root of x. So I have to think about this one. Cube root of x is the same as x to the 1/3, and so that's just a power rule. The derivative of that first part will be 5 times 1/3 x, and then we subtract 1, so negative 2/3. And then just regular second function times cosine of x. Okay, so let's just double check before we leave that we've got all the pieces. It looks like we have 4 pieces here, and in the middle is the plus sign that we need, and so that's good. Regular first times the derivative of the second, plus the derivative of the first. We really had to think about how we were going to treat this 5. It is a constant multiple, so it just hangs out at the beginning, and we take the derivative of that cube root of x. And then regular second part. All right, that looks great. The next thing to ask is, now that we know how to take the derivative of a product, what if we wanted to take the derivative of 2 functions that were being divided? So this is a function f divided by a function g, and we're going to use something called the quotient rule. And the quotient rule for derivatives says if you're taking the derivative of f divided by g, this will be g times f prime minus f times g prime all over g squared. And this is not a particularly beautiful formula. It does come from the product rule. It's just a corollary to the product rule. You can treat this quotient as actually just something like f times g to the minus 1 and then invoke the product rule, and you will get this. But we need some sort of way to remember this because we want to be able to memorize the order of everything. And a very common way that people think of this is low, like g is in the lower part of the fraction, d high, so derivative of the high part of the fraction. So low d high minus high d low, so high part of the fraction, derivative of the low, over low squared. So this is a very common way to remember the quotient rule, low d high minus high d low over low squared. Low d high minus high d low over low squared. Then you just have to remember you got to start with low. So low d high minus high d low over low squared. Let's try an example and practice this a little bit. So say that we want to find the derivative of, find dy dx if y equals the cube root of x over 1 plus x squared. This definitely applies to using the quotient rule. We have this larger function here that is the quotient of two functions. So we're going to step by step follow the quotient rule, which says take the low part of your fraction, just regular. So 1 plus x squared, and then take the derivative of the high part. So this is the same as x to the 1/3, and we just an example ago we looked and we decided that derivative of that was 1/3 x to the minus 2/3. So we've got this much of it, low d high minus high d low. Okay, the derivative of 1 plus x squared is just 2x all over low 1 plus x squared squared. That's it. So low d high minus high d low over low squared. So here we have a few more pieces, but we'll get pretty good at this. We'll get a lot of practice with different quotients that we need to take the derivative of. And this doesn't look like a shortcut, but it's way better than doing the limit definition of a derivative to this object. That would be a lot of work and very difficult and maybe not even able to algebraically simplify it. So this always works for our quotient if it is differentiable. So for this example, we're going to find f prime of x if f of x equals 5 plus x squared over 2x squared minus 1. This would be a great one for you to try on your own. So we'll just put the quotient rule over here so that we can reference it while we're practicing this example. But go ahead and try to find f prime of x of this using the quotient rule. Okay, so f prime of x will be low, and in this example, low is this guy right here. So low times the derivative of the high. What's the derivative of 5 plus x squared? That's 2x. Minus high, 5 plus x squared. And then the derivative of the low. And the derivative of that is just 4x. All over low squared. 2x squared minus 1, and then all of that squared. So low d high minus high, derivative of the low, over low squared. And so we found the derivative of f. For the next example, we're not given an equation for a function. We're given a table with certain values that we'll use to find the derivative. So the following table gives information about f of x and a function g of x. So we're going to say when x is 4, we know that f of x is negative 4, and g of x is 13. And when x is 4, f prime of x is, they tell us it's 0, and g prime of x is going to be 8. So this is all the information they give us, no equations, just this table of values, and they're going to ask us to find different derivatives. So the first thing that they ask us is if h of x equals f times g, they want us to find h prime of x. So h is a function that's just made by multiplying the two functions f and g together. No, not h prime of x. Let's find h prime of 4. And they want us to find h prime of 4. Well, here's f prime of 4, because here in all of these examples, x is 4. So f prime of 4 is 0, and g prime of 4 is 8. Should we say that it's multiplied these two derivatives together, 0 times 8, which is 0? No, remember that even though it seems logical that the derivative of a product would just be the product of the derivatives, it's actually much more complicated, and we have to think of the product rule anytime we take the derivative of a product. We're really truly going to use the product rule here, and we know that h prime of 4 should be f of 4. So f of 4 is this guy right here, negative 4, times g prime of 4, which is going to be 8 according to the table, plus f prime of 4, which is 0, times just regular g of 4, 13. Well, we can pretty quickly see that this just becomes 0, 0 times 13, and so h prime of 4 will just equal negative 32, and that's it. Okay, then say that they asked us, they say if m of x equals f of x over g of x, find m prime of 4. And definitely we're going to thinking the quotient rule here, and so we're going to, first of all, remember what the quotient rule is. Okay, so the quotient rule, we're going to pretty much just remember this low d high minus high d low over low squared, and we'll use that here. So low is g of 4, that would be m prime of 14. G of 4 is 13 times f prime of 4, which is 0, minus f of 4, which is negative 4, times g prime of 4, which is 8, all over g of 4 squared, so 13 squared. Let's double check all that. So g of 4, 13, f prime of 4, 0, f of 4 is negative 4, and g prime of 4 is 8. So this top looks good. Low d high minus high d low, all over low g prime of, or sorry, just regular g of 4, and that's 13 squared. So on the top, the 13 times 0 becomes 0, and then we have a plus 32, because we have a double negative, over 169. And that's the answer to, and that's how m is changing at x equals 4, 32 over 169. Okay, we're going to continue with the same example, the exact same table, and this time they ask, for this last part of the example, we're going to look at something a little bit more complicated. We're going to say if y equals 1 minus f of x, g of x over x plus g of x, we want to find dy dx when x equals 4. Okay, so this is something that is slightly more complicated. It looks like the overall structure, the largest structure, is that it's a quotient. Then we have like a little product inside and some other things going on too. And everything is happening at x equals 4, so that's good because that's the only thing we have a table for. So we're just going to treat this as a quotient rule, and we'll have to deal with whatever else comes up along the way. I'm just going to stick up quotient rule up here so that we can remember that overall structure. So dy dx when x equals 4 will be low d high. So low derivative of the high. Low will be 4 plus g of 4. Derivative of the high will be, the derivative of 1 is 0, minus the derivative of f of x, g of x evaluated at x equals 4. And we can't just take f prime of 4 times g prime of 4. We know this is a product rule. And so, but we can go back and use what we discovered in part A. Part A, we found out that the derivative, h was going to be the product, and so the derivative of h at 4 is just negative 32. So that means that the derivative of f of x times g of x when x equals 4 is negative 32. So this is negative 32. So this is low d high, low times the derivative of the high, minus high, which is 1 minus f of 4 g of 4. D low, the derivative of the low will be 1, because that's the derivative of x, and g prime of x, or g prime of 4. So 1 plus g prime evaluated at 4. And so we have low d high minus high, just regular d low, all over low squared, and that will be 4 plus g of 4 squared. So low squared. And we've done everything we need to do with the quotient rule. We just need to evaluate all these little pieces here and put it all together. So this will equal 4 plus g of 4 is 13 times 0 plus 32 minus 1 minus f of 4 is negative 4, and g of 4 is 13 times 1 plus g prime of 4, which is 8, all over 4 plus g of 4, which is 13, and all of that squared. So still just cleaning things up, 4 plus 13 will be 17 times 32, and let's see, 17 times 32 will be 544. So 544 minus, here we have a 1 minus negative 4, so that's a 5. No. Something else has to happen first. We have a negative 4 times 13, so 4 times 13, 52. So that first part is 1 plus 52. That's 53 times 9. And 53 times 9 is going to be 477. So minus 477 all over 17 squared. So 544 minus 477 is 67 over 17 squared, 289. Okay, so this is the final answer. We had this table here, and we were asked to compute the derivative at x equals 4 if this was our function y. We knew that the overall structure was a quotient rule, but inside there was this product rule, and we had already figured that one out, and so that's what made this negative 32 easy. That would have been a lot of work if we hadn't already figured it out. And then we just followed the quotient rule form after that. At this point, we just simplified all these numbers out. Okay, so we now know the product and quotient rule, so that'll open up a lot more functions to us that we can take the derivative of.